Next, we will have a panel discussion. I don't know if we have some time to organize ourselves. Can do it now. I will invite the speakers to have a seat in the front so we can start the session.
Oh.
Pass it around.
Yep.
If needed.
It's on.
Yeah. It might be off. Yeah.
Great. It's great.
So let me get your seat. Yeah, we should just start. Yeah. You want to stand or sit or up to you?
Fine.
There's one seat on that side.
Yeah.
Sit on each end or whatever. Or stand.
So when Ron and I prepare a set of questions, I think we will start with one question for Lee, which is, Lee, what do you think will be the most important innovations in healthcare in the next years?
What's the most important?
The most important innovations.
Innovation. I think in the next year, we'll see AI applications that will blow away your mind for every aspect of healthcare, whether it's the management of costs, whether it's the shuffling patients to different physicians at the level of operations. And we'll begin to see it informing doctors, as I discussed, about the choices and options they have for specific patients. So I think it's going to take a while to evolve the kind of things that I discussed. But already you can see AI applications that are absolutely going to fundamentally change how you manage healthcare. And I think soon they'll change how you practice healthcare.
Does somebody else want to address, or we can go to the next question maybe?
I'd like to build on something else that Lee said. The capacity that Lee is driving to look at thousands of features in your blood every 6 months for millions of people means that we will really have high dimensional data. We will find early signatures of diseases. If we can learn how to use those early signatures to offset the occurrence of the disease, we will turn preventative medicine into a transformation in medicine. And then Lee's right. In our country, we have grown on taking care of sick people. Our health system is bound that way. The transition to a health system in which preventative care becomes enormously efficient is going to be an enormous challenge globally, and Lee thought about that a lot.
Turn the green light on.
There we go. So I hope that Lee's optimism about AI is going to come to pass. When I hear anything about using AI to improve management of anything, it oftentimes comes down to improving cost and streamlining things, and that is not always a good thing. So hopefully in this case, it will be.
The question is about an innovation, but I think a challenge is just as important. Lee has pointed out that what do you do with the extra years at old age? And that even if you are healthy, then you can't play golf all the time. So this participatory part of the 4P medicine, it also includes the creating something meaningful for people to do. So if you can imagine that the people get retired, they are still healthy, there's something that they love to do, and they can share it with other people who are even older and maybe not so healthy, and have this kind of social exchange, and it's win-win for both groups.
You know, I'll add just a word to that. One of the outcomes of this scientific wellness that I've talked about is it's a fundamental thrust for pushing you toward healthy aging. And its major outcome is going to be to increase the health span, the number of years you're healthy physically and mentally, I think up into the 90s or so. And for many people, if they get into the 90s, they'll have had an extra 20 years of functional life. The question of what you're going to do with that, I think, is really an important one. And it comes back to the fundamental issue of education to kids and giving them a chance to think about the kind of opportunities they're going to have in the future and make informed thoughts about them. I mean, I've asked that question of a whole series of adults, and most of them, and you know, my point of view is you'll get tired of playing golf and tennis after a while. But most of them don't have any kind of answer to that question. They you know, just kind of shrug their shoulders. So that fourth P, that you have to participate in being healthy, and a part of that participation is how you use that health, I think, is very important.
Okay, we can move to the next question. So the theme of this session is called digital health. So as we know, there are big data, big knowledge, and the different models has bring into the table to advance the digital health. So we have a lot of experts here. I was wondering, the question is about mechanistic models has been developed for a very long time. Do you think today will be a good time to apply them in the digital health system? And if today is a good time, why that would be the good time?
Do you want to answer that, Sri?
Very, very important question. And I start to doubt about mechanistic models. I mean, you know, people know me, we love mechanistic model, ODEs or agent-based models. But all of us, I think we need to be ready to accept the fact that it might be that with AI, we don't need mechanistic thinking anymore. I mean, it's just mind-boggling for those of us that probe AI to the limit. And it could well be, and we have to be happy and try something new. That's where it is going. So, and it's still deeply satisfactory, and there will be problems where you need mechanistic models, but just training, very clever training. So it doesn't mean that we are dumb, don't need to do anything. We need to be very clever about the architecture of new AI models and training scenarios, and maybe they can do it. So for those that don't know, everybody thinks drug mechanism is important, but FDA just doesn't care. They know it, right? Efficacy and toxicity. You have a good ratio, and maybe the target, but we cannot figure out any mechanism. We're totally underdetermined. Now, who would have thought a GLP-1 agonist would reduce your craving behavior as opposed to just lowering your sugar? So we just don't know. And could be, we have to be willing to accept that.
You know, I'll add a word to it. I think the constraint on all of this AI promise at detail for really being able to understand humans is good data. And I think we're really short of good data. And a critical part of what Genome Health is all about is generating and aggregating that data in such a way we can collect from across the world and harmonize the data and have one structure that can be then interrogated with the appropriate human diversity to be able to make accurate predictions about racial differences among humans. And the racial differences in some diseases are absolutely striking. For example, ApoE2 homozygosity in Japanese is 3.5 times as likely to lead to cancer. And that's very high when you're old, as it is in Caucasians. And Caucasians, in turn, are 2.5 times more likely to get it, Alzheimer's, than African Americans. And the Hispanics essentially are not perturbed by ApoE homozygosity. So that's an incredible example of one gene that really transforms how we'll think about treating Alzheimer's in the future. So we need the range of data, we need the quality of data, and we need the scale of data. And we're missing all three of those right now.
So, so if you look in industry where digital twin technology is pretty pervasive or getting pretty pervasive, essentially all digital twins are mechanistic because things like preventive maintenance targets mechanisms. Now, the engineers have the advantage that they know the mechanisms because they're dealing with engineered systems. And but of course, in medicine, drugs target mechanisms. So if we know mechanisms, then it stands to reason that we should use mechanistic models. Now, we will never get at all aspects of a human using mechanistic models, right? We're the epitome of a complex system. And so we will never get to explain the various butterfly effects that exist, randomness in, say, receptor distributions on T cells or things like that, that will help us explain. And I think the ultimate structure of digital twins will be, they will be mechanistic as much as possible. And they will be made up of data-driven models taking up the rest of it. I think one good example is, for example, numerical weather prediction. Over the last 20 years, 25 years, numerical weather prediction has been getting extremely much better than it was. You can now predict the trajectory of a hurricane like the one we just saw for much farther out and much sooner. And the reason is because models have resolved lower and lower scales, and the data to calibrate them have gotten much better. But there will be a level at which, you will not get to it. You cannot chop the atmosphere up into cubic centimeter pieces and collect data from all of them. So at some point that will fail, but I think to the extent that we can use mechanisms, we should.
Yes, and the and is, in the case of the weather, we know ahead of time what the relevant variables are. In the case of organisms, where a given molecule has indefinitely many causal features, any one of which could turn out to be useful. That's just Darwin. It's just that it's not part of our theory yet. We really are confronting, it's certainly true in the time scale of evolution that molecules come to be used for quite different functions. It's a new question that I just tried to raise in the course of one lifetime or one disease. Does that also apply? Insofar as it does apply, it's a new question. Insofar as it's true that molecules come to have novel functions over a 30-year period or over a disease or whatever, we need to try to investigate if that's true and how much it may or may not alter what we're doing. And I think it's totally unknown.
So I have a question that I guess I can formulate it for Stu. There has been a lot of, Sui mentioned it and many others mentioned it, Boolean networks and all of these concepts about states and landscapes. But Stu, you put a challenge that clinicians and experts don't use those concepts. So how can we as modelers or people that are familiar with those concepts make them more relevant to medicine?
I don't know. This really just came to my attention literally yesterday. But here's this woman who's a perfect example. MIT undergraduate, residency in radiation oncology. She really knows what she's doing, and she doesn't know these ideas. So let's phrase the issue. We have all these ideas that we know, attractor, cell type, all that, all list them. We know a bunch. Why aren't they clinically relevant? One answer is they just can't be. Another is that we haven't thought about how they might be. If we've thought about how they might be, we haven't demonstrated that having thought about it, they can turn out to be relevant. And if they turn out to be relevant, people will take it up. So it raises another question. There is a deep, intelligent prejudice, it's not stupid, to think of the organism as a machine. We think of organism, we've thought of, this is really kind of interesting, just to tell you guys all of this. This is a fun story. When do you think the first mechanical clock was invented? This is more interesting than you think. Anybody got an idea when the first mechanical clock was invented? What?
50, if you're talking about not water.
And what's your year?
50 for a half-based clock.
1050?
Something like that.
Yeah, I think, yeah, well, the French had one, I think at around 1050, but otherwise the one is the Wallingford clock. Yeah, you know it. Yeah, it's either in Wallingford, it's either 1199, maybe 1320. And I want to believe the following, see what you think. Before a mechanical clock, you know, the cocks crowed and the seasons came and the tides went and pigs did whatever they do. And we lived in a world in which the number of hours per day differed in the summer and the winter. With a clock, if you were a reasonably smart modern person in 1390, there are clock towers all over Europe. And I think people started to say, wow, this is the world of machine. So I think we began to wonder, is the world a machine in the 1300s? Then you get Copernicus in 1543, then Kepler, then Galileo and Newton, and the world is a machine. It's a clockwork world. We believe that the world is a machine since Newton in 1687, and quantum mechanics doesn't change it. And the universal Turing machine is the epitome of a machine, right? It does exactly what you program it to do and nothing else. And what Andrea and I hope we've done is for the first time to say, maybe it's not. Maybe the evolving biosphere isn't a machine that keeps finding novel uses for all kinds of stuff, and finding a use for something isn't true or false. Classical physics is true or false. It's good enough for government work. It works. So if this is all right, there's something really big that we only begin to glimpse. It must have relevance for clinical practice. I don't know what it is, but it sure is exciting. Oh, on the long life, Lee, I just have to add, years ago, I don't know if any of you thought, what if you lived to be really old? And so I imagined I'm 3,030 and I'm applying to NIH for my 1,000th renewal. You know, it's a 3-year grant. It has to do with what do we do with all that life? And here is my grant application. It begins in our preliminary results. Can you imagine living to 3,030 and you're writing NIH about your preliminary results? I'd rather not.
So when I was listening to you,
Oh,
when I was listening to you talk about this woman you met on the plane, my first thought was, well, how would it help her in her daily practice to
Yeah.
understand attractors? And I think it might not. On the other hand, you know, as Wittgenstein once said, that which you cannot speak about, you cannot think about. And so if you're missing the language of mathematics, it prevents you from viewing the work you do at a bigger level in new ways. And so certainly training physicians in mathematics, just like Plato argued for training philosophers in mathematics, not because it was important for philosophy, but it helped you develop a vocabulary that allowed you to think in out-of-the-box ways. And ultimately, the role of mathematics for nature and application really is just as a language, not necessarily themselves. So I totally wholeheartedly agree with you that this woman should learn about attractors, as all of us.
You know, I told her, but I really,
Here,
and she didn't care. But she was awfully nice.
Thank you. So our next question is, when we are developing the digital twin system, we know digital twin system is not only about models. There are a lot of engineering part, data part, as Lee mentioned. So I was wondering, from different aspects, for example, we can start from engineering part, which Oli has also working with our team to develop the dashboard or communicating with hospitals. What do you think would be the most important and challenging part for developing the digital twin system from the engineering point of view? So this question point to Oli, but there are all the other expertise from the panelists.
Could you repeat the?
Okay. The question is, from the engineering point of view, what do you think is the most important or challenging part in developing the AML, the digital twin system?
the AML digital twin.
Yeah, we can start with AML digital.
Well, it relates to the previous question, the common language. I would think, well, I was an engineer in the beginning and then tried to work with biologists first, and I felt like it's a light year away from me. Then we started working with medical doctors, and there's another light year that you have to pass. I would like to use this kind of allegory that you have a Christmas tree and you want to decorate it. Then you actually have to agree that this is a tree and what is the trunk and what is the top and what are the branches. And then you have all these decorations on the floor. So all the time you have to know what the other person is talking about, and then it's so helpful to have some kind of illustration or joint context that you can refer to, and not just because these are really complex issues. So you have to, in order to understand, you can say that they read these 3,000 papers, and then you understand. We have to have something that we can discuss about, and now we have a lot of tools for that, visualizations and everything. So that has to be somehow integrated into all discussions, and that has to be a part of the education, I think, so that students from different disciplines learn to use these tools, because otherwise they just talk and get tired because nobody understands anything.
So on your question on the challenge, I think for me, one of the biggest challenge is figure out what is the level of abstraction. Many people talk about multi-scale and so, but it could well be that we don't need molecular scale for cancer, but let's say we monitor all the cell types in blood or somewhere and the relative proportions and their dynamics. Maybe that's where our optimization should lie. So we might be way too granular and hitting the right level of abstraction. I think it's very hard. We can model cell population dynamics, like clonal dynamics. That might be enough. So there was this old example of this guy, pathologist, who was dismayed by the entry of molecular biology in cancer. And they'll just look at the radiologically modeling the tumor size. And the saying goes like, you cannot try to understand traffic jams by dissecting and understanding the combustion engine in cars. So just model traffic flow, right? And that could be possible, and that could easily fit into a digital twin, but not necessarily at molecular level.
Yeah, and the last question we prepare, I think it's for everybody, but I guess I can start with Sui. It's from your previous discussions with Ilya, which of them you remember that got you excited and it was helpful for your research?
I think it was an unconditional embrace of theory and not being offended if everything is wrong, and then be very practical, right? That's the way it is in medicine.
Lee?
I think the thing that continually impressed me was his enormous curiosity. And it was about any kind of topic and object you wanted to discuss. And I found very few people that even began to approach his level of passion for learning.
I'll repeat just how much I loved Ilya. We published in 2004 the paper Activities and Sensitivities in Boolean Nets. That was on the Boolean derivative. That was entirely Ilya, and it was a transformational paper. He just kept having brilliant insights and humor and drive and made things happen, and riding his bike.
Yeah, I think along the lines of what Lee said, Ilya always made you feel like he actually cared about what you had to say, and that does not always happen.
Well, if you play chess for fun, not in order to win, then you do it for fun. And I felt like with Ilya, when we interacted in science, it was the main thing was that it was fun. Doesn't matter how serious or difficult it was. It was sort of more fun if it was complicated.
So I was wondering, are there any questions from the audience who want to ask the panelists or answer the last question we just asked?
Lee, early in your talk, you mentioned the transition from wellness to disease and the fact that you had found protein markers that were part of indicators of that transition. What do we know about those protein markers? Are they related to pre-existing proteins? Are they perhaps fragments or modified forms? Or are they proteins that are not expressed until the appearance of the
No,
transition?
they're perfectly normal proteins. And as I said, often the proteins you find in those early signals map back into a network in the cancer disease that's been perturbed. So in the first one we did, for example, we followed 5 proteins across the 4 samples that existed out to 2 years before diagnosis. 3 of them we could beautifully map into typical networks for stage 4 pancreatic cancer. So the key of the proteins was they told you where you wanted to go to get started on that early preventive reversal.
Hello, my name is Alex Ratushny. So I'm from ISB, and just I have so many things to share. But the one thing, it's not a question, but a comment. So I came from the middle of Siberia, and one of my first book chapter was about Stu's actually work back in 60s. So people are talking about attractors, maybe not all. So so another thing, now I'm just with the transition with the postdoc at ISB, and then now I'm kind of in the big pharma, Bristol Myers Squibb, etc. So the one comment I'd like to say, so the ice has broken. Yeah, so the FDA and other regulatory agencies, they're very seriously considering those mechanistic approaches, and it's a part of the filing and the communications with them from the kind of those kind of principal investigators and the clinical trials in terms of some aspects, not everything, and it's mostly like supportive rather than decisional. But I guess we're getting there, and it's actually very seriously kind of considered. And there are the guidelines appearing, there are the meetings there. So I'm happy to be part of it, and I think ILIA and ISB played a role, and it's actually evolving, and it will probably gonna go and will be actually more exposed and more, I guess, like not the completely kind of standardization or like everywhere, but I guess we're getting there, and we should actually continue pushing through and to not just like rest, but just go and just continue doing that, what we're doing here and in other centers. And thank you again for this wonderful meeting.
Well, you know, I'll make one obvious comment on that, and that is the textbook on systems biology and systems medicine we wrote with Illy and Sui and others, I think is going to be key, one, in hopefully bringing to medical students the kind of discussion that we've had here, but two, from it, we can actually abstract beautifully courses that can be given to higher level students in K through 12. And ISB has actually done one such approach using the two medically oriented systems biology chapters we wrote. And that course has been tested now for going on 3 years, and it's been spectacularly successful. So we're going to expand that out and then think about doing a modification of it for doctors. So I think education is the key to getting the word out. And I think we all can play a role in doing that.
I would love to thank you all so much. This is amazing. My question is partly for Sui, partly for Stu, partly for Lee. In terms of Ilya's work in criticality and the question of why and how medical interventions and practice in a daily basis might be able to use that concept as a higher level of abstraction in terms of attractors. For example, stress management is something really huge in terms of what the participant can engage in terms of how they sort of maintain some level of balance, perhaps. I just wanted to ask if there's something we can do to celebrate and extend Ilya's work in criticality to the behavioral, perceptual, participatory aspects of finding balance in one's system as part of personalized medicine in the future.
Thanks, Kate. I think that's very important, and we take it for granted that when we talk about mechanism, we always mean molecular mechanism and gene regulating each other, but criticality exists also in just anything that relates to each other in a network can exhibit critical behaviors. And for example, if you all these variables in the ICU, and people doing that now, you measure blood pressure, pulse, everything, potassium, sodium, and there's a time cost. To have that already, you can build a digital twin without a mechanism, right? You just put in relationships and so far pretty mindlessly, but now we can induce or insert thinking about critical dynamics. So I think it's going on, and we should keep that in mind.
Beautiful.
I'd like to comment that well, the system doesn't have to be really complex in order to have meaningful attractor properties. So you could play with completely higher level variables, like, and just a few of them. I will tell an example. So visited England in the 90s by car, and I spent six months there. And in Finland, where I live, then you go to the gas station, you always have a windshield wiper at the gas station. In England, there were none. So we have like basic properties. We have cars, drivers, gas stations, and the windshield wipers. This is the genome, but the phenome is completely different. There's no wipers. You have to buy one. And I wondered about this, and they said that if they put a wiper there, then it will be stolen. Of course, it will be stolen because there's no wipers in any other of the stations. But that's an attractor where you get into it. And I tried to propose that why don't you use really large and dirty wipers? Nobody wants to steal them. I don't know what is the situation now, but the point is that it doesn't have to be so complicated and go to the molecular level necessarily. It could be like psychology.
I'll give you a really clear example of that too. I mean, criticality in part is this balance between stability and responsiveness, okay? And I think resilience is just that. And one of the big things in healthcare we want to figure out is resilience. And the question is how to promote both of those features of criticality. A stability so it endures, and the responsiveness so it can respond to a diversity of challenges and so forth. So analogies like that, I think you can put in books and anybody can understand them, and they're very powerful and convincing. And in just what Sui said, that probably can be dissected at a much higher level to optimize the features.
Thank you all for the comments. I think the conversation will continue for many years. Thank you all the speakers for the wonderful talk for the morning session, and thank you.